Afternoon, everyone. Thanks for coming along. Packed house. This is the very first bank flagship seminar series, which is a big deal for the bank as part of our drive for greater openness, transparency. These are going to be very high-profile events. All of this is being live streamed on YouTube, whatever that is. At least the formal presentation part, the Q&A, we're off screen then, so you can say whatever you want. So, and the idea is that we invite in the brightest minds from the whole world and ask them to talk about the world's most important issues. And in this respect, it's a particular delight to welcome to the bank Nassim Taleb. I can't think anyone much better than Nassim to kick off our flagship series. I first came across Nassim's work, actually, a long time ago, Nassim, before you were famous, in fact. In 2002, I think Malcolm Gladwell did a New Yorker piece. At the time, you were a trader, and Nassim's trading strategy was basically to trade on the fact that tail risk, extreme events, were not being properly priced. And that ended up being a very profitable trading strategy. And out of that really grew the philosophy that's underpinned what are now three famous best-selling books. The Black Swan, Fooled by Randomness, and Anti-Fragility. And a fourth is coming down the pipe, I hear, from Nassim soon. Those books coincided with the global financial crisis. It shouldn't have taken a global financial crisis to bring those ideas to life, but as we had one, good that we make good use of it. And we have, because some of the concepts in Nassim's books have now entered the popular lexicon. Tail risks, black swans, anti-fragility are now the terms in which we conduct debate about risk. And that is testimony to the power of Nassim's ideas and his writings. So we at the bank obviously have a big interest in risk. We're in the risk business too. So it's a particular pleasure to welcome Nassim today. And we're greatly looking forward to what you have to say about risk. So please join me in welcoming to our first flagship seminar series, Nassim Taleb.
Sorry, I'm extremely honored to be here, and again, I'm not used to being on the inside. Usually I'm on the outside barking, so maybe that would, it's a different attitude. I have to be mild-mannered and understated and all kind of thing, whereas before I was aggressive, you know, hey, this is wrong, stuff like that. But I'm extremely proud to be here, particularly that with like-minded people. We, you know, particularly Andy's thinking about simplify things and focus on heuristics. And I discovered that we share the same collaborator and friend, Gig Renzer, who actually was a cause of this idea of heuristic I'm presenting today. So it looks like we come from the same school. Finally, there's a school of thought of how to do business in the real world that is less complicated, more effective, more entertaining, especially. All right, this counts more. So before getting to fragility, can you hear me? This works. I'm going to start with the boring part and the unpleasant part, statistics. Okay, so by tearing down what exists in terms of statistical thinking on statistical ground, by showing that it's not rigorous, that what you hear, a lot of people talk statistics, but it contradicts the foundation of statistical thinking, which is significance. All right, know the significance of what you're talking about before you talk about something. So this is part of this project we call Doing Statistics on the Fat Tails program, where you had to revamp all estimators. So let me tell you the story. I started dealing with fat tails, and about 99.9% of economists I've encountered would reply, Nothing new. We know a lot about fat tails. We know they exist. Pareto discovered fat tails. This guy discovered fat tails. It's not the point. So my answer is, the first thing is, why do you keep blowing up if you know about fat tails? So visibly you're not. There's schizophrenia or some element of, I don't know, what you call it, incoherence or something. And the second question is, why isn't econometrics more effective than astrology? Basic fact, if you're a statistician, you worry about statistics, so you worry about your own statistics. Why does it work out of sample slightly worse than astrology, right? So visibly, there's got to be something wrong. And the third question is, why do you use mean variance? If you understand fat tail, it contradicts everything you're doing. So visibly, you don't understand fat tail. The point is that it is not changing the color of the dress. It's not saying, hey, you know, it's fat tail, okay, it's a different class distribution. It's a different way of thinking, different convergence mechanism, different, and now we're going to see different procedures and different estimators. And then you realize once you do it rigorously that a lot of things become easier and a lot of things you can reject. You can just close down econometrics for some, we're going to reasonably show, but you can open up other things. The first thing I'm going to talk about, the central thing about human knowledge, is the law of large numbers. Without the law of large numbers, you can't talk about the sun rising, you see, tomorrow. You can't talk about English pudding being something that is not attractive to foreigners. You cannot, but other things are attractive to foreigners, visibly, a lot of things. That the English weather, you get the idea. Without law of large numbers, okay. So what we have here is, to the left, is we have what we call a thin-tailed Gaussian, whatever you want to call it, probability distribution. And to the right, we have a fat-tailed probability distribution. And actually, this one I picked was the most known probability distribution, which is what? What's the most known probability distribution? Or thing people talk about casually, particularly on the internet. 80-20. This is what you have here on the right, okay? So on the left, so you see how fast the first one converges. In other words, you have some observation, you know what's going on. And you see how slowly the second one converges, okay? The mean exists for both of them, but you reach it very, very slowly in the second one. Let me show you the speed, actually. And you assume they have the same mean. The blue is how the 80-20 converges, and the yellowish one is how the Gaussian converges, all right? So even if you start with the same mean deviation. So here I'm going to ask you a question. I have a Gaussian, and I have 30 observation. How many more observations do I need? In other words, the n needs to be for Pareto 80-20 to have the exact same error on the mean from observation. How large your average, how large a sample you should have to track the average with the same error rate at 30 for a Gaussian? Someone can tell me? 50, who said 50,000? Come on, who said more?
Higher.
Okay.
What was that?
10 to the 13. I don't think it would, you know, the market would have reached that price, okay? 10 to the 13. Does it tell you something? It tells you that the mean is not estimated from sample. You got to do something else to estimate it from sample. Okay? So, I mean, this is standard, usually convergence theory. So, it is unrigorous for a fat-tailed process to derive the mean from small samples. It is unrigorous to make statements because they don't have the significance. It's very simple, all right? And this is basic statistics. People forget the basics. They go, okay, now, next trait, all right? Have you heard of a measure? How do you know how fat the tails are? Conventional, what you learn in school. Excel has a function for it. What is it called? Sorry? Kurtosis. Okay. If I have 10,000 pieces of data, n of 10,000, okay, in the financial markets, and I take the largest observation, visibly the largest contributor to kurtosis, how much of the total over 10,000, which is about 50 years of data, How much of the total do you think you're going to be represented by the largest deviation?
By what?
By the largest deviation. 1 in 10,000 will determine what percentage of the kurtosis. That we know that people talk about 1%, of the people on a planet have, 50% of the wealth, some kind of stuff. All right. The same reasoning. 1 in 10,000 will have how much of the kurtosis? There you go. For the S&P 500, 82%. Okay, that was as of 2007. I think the numbers have changed since. It's so unstable. Maybe if to take the top 3, you get the same. That's the 60 years or 55 years until 2007 when I did that. For silver, same. These numbers are 2007, 90-some%. What does it tell us? It tells us you cannot use standard deviation. You cannot use variance because as a kurtosis is what? It's volatile, it's a variance. Okay? It's too unstable, so you don't know it. How can you use a measure if you don't know its error rate? We're on the wrong track. Okay? Now, okay. More bad news to hit. Inequality measures. Have you heard of Picatistas and Picatism and stuff like that? Okay. What do people use to measure inequality? They use a Gini or centiles. Okay? Now, it so happens that on the fat tails, and effectively Wass's fat tails, you cannot measure it the way they're measuring it. Let me show you where. This is a little complicated, but the error, if you have 2 countries, okay, I have 2 countries, I'm likely to find a Gini of 70 on average between the 2 countries. If I make them one country, the Gini will be higher. That's the effect of fat tails. So in other words, even something as silly as a Gini coefficient, all right, is improperly measured. And to measure it properly, you need to do other things. Measure the tail alpha, and that's another talk. If I'm invited 10 years from, last time I was here was 9 years ago, so if I'm invited 9 years from now, maybe 8 years hopefully, if I'm lucky, then we'll talk about that, okay? So we have problems really with fat tails because your entire thinking and your entire methods have to be revamped, okay? So this is pretty much what we can say that it's a social science statistical toolkit. It's pretty much like trying to build a cathedral, like St. Paul nearby, it's beautiful, no? Using these, all right? You're not going to go very, very far. And effectively what's slowing us down is the basic foundation of statistical rigor are not met. That's it. Simple statement, okay? Now let's go next. So before we hit, so good news is that we know where the bias is. Let me give you one you see, when you have a distribution that is fat tail, that's one-sided, you tend to know that the mean is determined by tail events, and you're not likely to have these tail events in your sample, no? So they are fudges to figure out what the shadow mean is. But let me make you something this is alpha, the tail exponent. As alpha becomes smaller and smaller, more and more of the observation fall if you're, like this one, is above the mean. If this one is left-tailed, so in other words, when you look at bank performance, close to 90-some% of the observations fall above the mean. Because one tail event one day will bring back the mean. So you realize, we know that. If you know that, then you can look at a histogram of the return and add these bad observations. Or there are other stuff called tail extension. So we know how to work with it, provided you accept that you're no longer dealing with a thin tail distribution, and you're in a new family of distributions that require different thinking, different methods, different rigor. And also not make statements off of small samples. So this is the asymmetry, is visibly, if it's one tail to the right, samples, like in entrepreneurship, samples will underestimate the mean, and vice versa on the left. And we know how to work with it. Something I call shadow mean. So we're working with violence, okay, violence on a planet. And people would measure the mean. I say, no, you unintelligent person. Sorry, I can't. I got to be, I'm recorded, so I have to be extremely mild-mannered. People would measure the mean. I say, no, you unintelligent person. Sorry, I can't. I got to be, I'm recorded, so I have to be extremely mild-mannered. I'm from the inside. I don't have to prove anything. No, so I got to be mild-mannered. So no, you unintelligent person. Contrary-wise, I have to prove anything. No, so I got to be mild-mannered. So no, you unintelligent person. Say, okay. You cannot measure violence, the rate of violence, for example. And this is an article which is published on violence, published with the co-author Pasquale Cirillo. There's the sample mean, and there is the maximum likelihood mean we can measure in some technique. And look at the difference, that the true mean, the statistical mean, is 4 times or 3 times what you observe. We can pull these biases. We can actually look at the P&L of a bank and figure out, hey, what? They make that much? No. They make a third, you see. Or look at the performance of an industry and say, no, the real mean is above, because all you need one large observation, which falls within statistical likelihood. It's just like, think about it. If I have 10 years of data, I'm not going to have the 100-year flood, no? That's basically the central method. And what's missing is that tail that will increase your mean. You see, that's pretty much how to think about these things. One more thing about non-parametric statistics is that the regular on the x-axis is what happened, let's say, at the period t, and you look what happened t plus 1. You see the regular events tend to predict regular events. Very nice, except that we don't care much about regular events. We care about tail events. So tail events don't predict tail events. If you look at history, you will have a huge number of tail events without a predecessor in that time series. So in other words, naive fitting histograms won't get you there. But we have a huge number of tail events without a successor. You see, in both cases, all right, other mistakes. What impact does this have? Is that, okay, so summarized, so we have fat tail distribution, we have fit tail distribution. You got to think about them differently. And the people, the minute they learn a little bit of statistics, they start talking about rationality. They start saying you're overreacting to risks. So we take the case of Ebola, all right? Ebola is something that, and some people have complained in the United States that we worry more about Ebola than other problems, say people who are murdered by their brother-in-law while taking a shower, for example, all right? But yet more people yet, okay, your risk of being murdered by your brother-in-law while taking a shower is higher than contracting Ebola, for example. They come up with these idiotic statistics. Or more people have been in bed with Kim Kardashian than have died of Ebola in the United States. So this is a statistic. Really, someone has actually in newspapers. So the public communication of science, the minute they try to teach people science, they fall into the trap of someone who doesn't know what they're talking about, trying to talk about a subject that's vastly more complex. Stay at the grandmother intuition level. It's a lot better than play a little bit of scientist. Effectively, it's very rational to worry about Ebola because Ebola is a fat-tailed process. When you look at something from the tails, the probability of 1 billion people spending time in a bed of Kim Kardashian, as you can say, is safely 0, all right? But the probability of, the ratio of these probabilities, the ratio of Ebola killing 1 billion people is much higher than the other one. So a different class. The probability of people dying in their bathtub doubling year on year, because it's a thin-tailed process, is 1 in 10 to the 20 probably, okay? Whereas the probability of the number of casualties of Ebola doubling is not in the same order. You see? So that's how you got to look at classes. So some thick-tailed thin classes versus thin-tailed classes, some are vastly more dangerous than others. For example, if a plane crashes, it kills the passengers. It's a thin-tailed event that's disastrous, horrible. We should worry about it. But it doesn't kill every single passenger who ever rode on a plane. You see, it doesn't kill the whole of humanity. Whereas when banks lose money, they tend to lose, as they did in 2008, more money than ever made in the history of banking. You see, then you have to worry about two different, you cannot compare thin tail to fat tail. So using Ebola, tobacco, saying, look at alcohol killing, where you're worried about Ebola is irrational, because the number of people dying of alcohol cannot double. The number, this is a multiplicative process. The hallmark, you have to panic even more. You're tempted to panic, panic twice as much when it's a fat tail process. We don't have many of them, and it pays to be paranoid with them. Okay, so this is the first part about what's wrong with our approach to statistics. And I guess nobody here got angry, everything went right. Okay, next, the good news is that we have different ways to look at the world, okay? So instead of focusing on the statistics, you can focus on the property of the object. This is a glass of water. We know it's fragile, no? Why is it fragile? What is it that everything that's fragile, all the things that are fragile, have something in common? What is it?
Rigidity.
Sorry?
Rigidity? No. Rigid? Sorry.
No, the fragile things are fragile, have in common fragility is tautological. So let's go one step beyond. Sorry? Rigidity. No. Rigidity is not common to all of them. Sorry? No.
When they are in the degree of entropy.
No. Oh, he didn't. We use entropy, getting close. But let's put it. That's much simpler. Much simpler.
Uncertainty.
What's that uncertainty? Getting close.
Irreversible?
This is very good, but this is. We'll get to it later. It's a ruin is a different. With this.
Randomness.
They don't like all of these things you mentioned. They don't like volatility. All right. Does this like volatility? Yes or no? No. It's like a short option portfolio. Okay. So, so let me state now where we're going to go to, and then little by little we're going to do some good work on figuring out that if you don't understand the world, it doesn't matter. You care about how things react to it. All right. So the rain in Zimbabwe is not a random variable I can easily measure, but I couldn't care less. All right, visibly. You see the idea. So how things affect me in a certain way that we're going to now discuss, and that's much easier to gauge. And how uncertainty can affect this coffee cup or this water cup is very easy, much easier to figure out. Okay, it's a very simple heuristic. This is what I'm going to get to. So let me give the fragility logic, the whole thing in one. In case I die now, or something happens to me, or someone, all right, or there's a riot or something, I have to leave. This slide summarizes everything. So first statement is all fragile objects dislike disorder, or the disorder cluster that will define. If you accept the definition, then fragility can be expressed as aversion to volatility. And we can technically work with that very easily, because you take, even if the distribution doesn't have standard deviation, we couldn't care less, you divide x by s, or you see a random variable x, you transform it into x divided by s and perturbate s, and that widens the distribution for all distribution. That's pretty much what would happen. I mean, for something called location scale family distribution, but pretty much we can generalize for the tail for all distribution. Second point, everything that is averse to uncertainty, volatility, all these things entail, has to have a nonlinear concave response. Okay, let me explain something. Is someone an option trader here? Okay. If you're short volatility, would you be harmed more if the market went down 10% than twice if the market, went down 5%?
No. Well, you'd be harmed more.
If you're short volatility, are you an option trader? Okay.
If you're short vol, you get your P&L will be negative, much more significantly than a non-linear range.
Exactly. Very good. So you confirm what I said. So I'm not dreaming it up. I'm not. We have confirmation from two option traders. All right. So 10% is worse than 2 times 5%. Okay. So that's all right. That's acceleration. The same thing with the coffee cup. We're going to see. Everything will have that acceleration. Okay. Then, so fragility requires asymmetry. All right. That's simple logical argument. This is all logic. All right. Nothing complicated. Fragility is detectable, even measurable, because then you can detect a reaction locally. You can generalize from detecting local nonlinearity, and then fragility is dose dependent. That's it. So let me walk through this. if there's an option trader in a room, which P&L of these four is short volatility? The top left, okay? It's exactly the same P&L as this glass of water, the glass. All the variation are going to be to the downside, you agree? So if there is a variation, it's more likely to be harmed, okay? So if there's an input, whatever it is, either indifferent or going to be harmed down, you agree? All right, except that for the coffee cup, there's no small variation, it's just one down or nothing, okay? All right. So this P&L is patently fragile. It's shared by all fragile objects. That's in time series space. The one right below it is a robust. You see? It's sort of like some of the friends I have in Brooklyn. They couldn't care less, all right? So they're robust. They couldn't care less. They have no emotional, all right, fragility to anything. They couldn't care less, all right? That's robust. And then, of course, we have two things here we worry about later. In probability of payoff, the robust has thin tails left and right, and the fragile has a thick left tail. Okay, that's very simple. So now we can re-express it mathematically. If you're bored with the math, ignore the math, or think of the beach or Brighton or whatever it is. Okay, and like within 10 seconds, it will be, we'll go to a more verbal thing. So sensitivity to S. Forget the math here, okay? And we can really phrase it this way, as the solar cluster. If you don't like one, you don't like all of them. Because all of them are expressed in this S, all right? Okay. S is, you divide X by S. It's very invariable X by S. And you see what impact it has. Changes in S on the tail. That's it, okay? And then there are other ways to approach S, non-parametric. The ways is one is a tail, S what happens to that integral below. You can express it in a lot of ways, but you get the same result, which is the following. Transfer theorems. That convexity, if you have a convex response to a random variable, say the S&P 500, and I have a function, my P&L is a function of the S&P 500. If I'm convex from that, okay, then more uncertainty about my own P&L gives me an increased right tail. All right, in other words, I don't have a left tail, I have a right tail, and I like volatility. Okay, that's just why this is tautological for option traders, but you can generalize outside. If I'm concave, then it's a reverse. Okay, that's simple, no? Okay, so now, the thing that is interesting here is that let's talk about X and f of X. X and f of X are different animals. X is the rain in Panama. All right, f of X is my P&L. All right, so visibly they're not coupled directly. You agree? So there's no reaction. But X can be the S&P 500, and f of X I'm longer call. X can be the whatever it is, the unemployment, and f of X is my budget deficit. Okay, so you realize here there's always like a rigor studying the statistical properties of X, and not those of f of X, and we know how to bridge them. Okay. Basically, if you're convex, look at it. If you're convex, if f of X is convex, then there's probability distribution of X. Look at that f of X. It has the right properties, which is what we call anti-fragile, right? And it could have the reverse. If it's concave, then it moves to the left. We're going to see more of that later. This is so far not very entertaining. I can see faces that are quizzed, but we're going to drill the same point in from different angles. Nonlinearity as necessity. Go back to the coffee cup, okay? Let me explain why everything fragile has to be nonlinear, okay? Now, I don't know, did someone, how, you can jump from St. Paul, no? Do people commit suicide frequently from there? No? What do people kill themselves here in London when they lose money? I mean, this is, all right? No, I mean, just, it's for information. Or no, my P&L is okay, I'm not. What do people do in London? Sorry? No, it's not. I mean, in New York, they used to jump from the Empire State Building. Sorry? Okay, so let's play this thought experiment. If I jump 10 meters, I am vastly more harmed than 10 times 1 meter. You agree? It tells you something. Aha. It tells you that I'm physically, I have a concavity to height when I jump. Okay. That's simple, all right? So pretty much every fragile object, because if I were linear, and this is a necessary relationship, if I were linear to harm, okay, if 10 meters, jumping 10 meters is 10 times the harm of 1 meter, not a lot more, then 1 meter has to be 10 times the harm of 10 centimeters, you agree? And 10 centimeters is going to be 10 times the harm of 1 centimeter. It means your linear harm, if you die at 10 meters, it means you have to lose a piece of your flesh, all right, every time you walk to work, you see? But you don't. You're insensitive to small shocks, but harmed by large shocks. So necessarily you have this curve up there. So we have an option trader in the room. It reminds you of what? The short gamma. Short volatility position has this shape, you see? So every short volatility position has to, why do we have accelerated harm? Because if you had a linear, in other words, if you lost a billion, all right, if there's a 10% move, all right, and you were linear, you'd lose 100 million if there's 1% move. And 1% moves are vastly more frequent than 10% move, you see? So it means that you'd have a P&L such that your bosses will all have heart attacks, not just one. The whole bank north of your boss, and maybe not yourself because you're an option trader, you don't care, all right? Everybody would have heart attacks, all right? So it means that you have to have risk that blows you up, you have to be intact for small variation, okay? Just like this is intact for small variation, otherwise it wouldn't be here. We'll get into this argument mathematically later just to dress it up, okay? So you see the idea. So all you have to do as a condition, so all you have to do is find the place at some point you have acceleration. Necessary. So Fannie Mae, 30 basis points, 40 basis points, you don't hear about them, all right? 150 basis points widening of the spread, all right, this thing collapses, all right? Visibly, you have nonlinearity. It is necessary. Okay, let's continue with the reasoning. Let's go back to coffee cup. So for those of you who like modeling, what you have up top is a coffee cup, all right? If I double the harm, at some point I break the coffee cup. You agree? All right. But let's say that now, I don't know if is it filming me. Can I walk to the screen? Use my point with my finger?
I think so.
It's okay. All right. So this is a coffee cup. I increase the intensity. Visibly, you have some kind of discontinuity here in the derivatives, all right? But so let's make it nicer mathematically to see the connection. These are all coffee cups. Some break, some are more linear. They eventually have the same, start the same, they end at the same, you see? But we can control one parameter here. This parameter, okay, Greek letter. That when I increase that parameter, it becomes nonlinear, okay? When I decrease the parameter, it becomes linear. So think of a bank, here it falls apart, okay, but before it doesn't fall apart. And notice also you concave before you break and convex later because you couldn't care less anymore. You see, when you're dead, you're extremely robust. And when you're bankrupt, you're extremely, you go back, you sleep, you don't have to worry. You don't have to worry anymore, all right? Okay, so this is pretty much the inverse S curve in nature, and let's see what we can get out of this. So what we get out of this is the following: a low kappa produces something like arc sine. You see this? It means that most coffee cups that are like that, you have nothing in the middle half cup. It's either intact or, it's fully intact or in a trash can, you see. Do you agree? So if we humans were more linear to harm, it would be either, the way we are, we tend to be either intact, all right, or in cemetery. You see, there are a lot of cemeteries in London you can check, right? So, if it were linear, you'd have most coffee cups half broken, and most humans, it would be the majority of humans you would see, would be half broken, as well, someone missing an eye, a nose, this, you see? We don't observe that. And banks would be half, completely half, we don't observe that. You tend to observe things that are intact. So, if you observe things that are intact, then necessarily these objects that you're observing that are either intact or dead have to have nonlinearity. This is simple logic, all right? So if I want to explain it to option traders, they tell me, "Ah, you know, you write books about this?" It's so simple, okay? So it's once you go away from option trading that, hey, it becomes complicated. So now in words, all that has bimodal distribution of the type above is necessarily nonlinear, okay? And the fragile necessarily locally indifferent to small variations. And banks that blow up from unexpected shocks are necessarily indifferent to the small variations. Let me, same variable. So let me take this. This visibly, you know how many earthquakes there are felt in London every year? Tiny, 2,000, come on. You guys tend to bid low always, all right? Like 50,000 there, 2,000, about 2 million of them, all right? But they don't affect this. So cumulatively it doesn't affect it. But a little more, and it breaks. It's the same thing. Okay, so by now you got the idea that what we define as fragile has to have one property coming with it, which is nonlinear in response to the variable that breaks it. Simple. From that, as the option trader realized, it's so boring. Yeah, I knew that, all right? So from that, we can issue rules now. We can do metrics of detecting nonlinearities to simplify so we can, so Professor Gegenrenzer can be happy with us because we found simple heuristic. And what Professor Gegenrenzer does, he says, you know, most people who are rationalistic want to replicate a baseball player would make someone solve the differential equation to go catch a ball. But in fact, how do baseball players catch a ball? They have a gaze heuristic, which is what? You just look at the ball, and you're rather looking at the ball, and you're going to catch it, you're going to be at the right angle to catch it. So nothing too complicated, it's a very simple heuristic. So we're going to have to look at the only thing that works in the real world are these kind of heuristics. Simple rules that you apply, all right, that effectively save you from a lot of analysis, that have justification. Anyway, so let me give some other stuff coming with it, because with a package I got to make things complicated so people take it more seriously. But all right, so options are very convex to tail events. Okay, so because options are very convex to tail events, there's a constant error in the literature to look at options and say, well, you know, they don't make money. You look at these are the lambda equals 0 is at the money, 10% out of the money. Lambda of 20% is 20%, 20 sigmas out of the money. You see how concave they become. In other words, if you're long an option that's 20 sigma out of the money, and there is a 20 sigma event, you stand to make several 100,000, all right, years of time decay.
Just need to have enough capital to last that long.
Sorry?
Just need to have enough capital.
No, but because they cost pennies. Well, conversely, let me tell you one thing. The banks lost $5 billion, all right? $5 trillion in the crisis. From what? From short tail events that made them 6 basis points, largely. So you got to think about it. Most people don't realize how cheap it is to buy these instruments because they're assuming they exist. Another one, explosion of volatility. If you have a 10 sigma out of the money option and volatility multiplied by 2, it multiplied by 27. If you have an at-the-money option, it's multiplied by 2, by doubles, all right? So if volatility doubles, for 15 sigma, it makes 300. And you see how convex it is, that if volatility is multiplied by 4, for a 10 sigma out-of-the-money option, you're multiplying your value by 140, all right? Now, I don't know how many of you have market memory. How many times did the VIX go up fourfold over the past 20 years? Many, right? So that gives you an idea of you know, but you can detect the concavities and convexities very easily. So this is, so far I presented the problem, namely that statistically we have no clue. And the very idea of calibration, when you walk in the morning, say, I'm going to, okay, tells you that they have no clue. But if they understood science, they would say, a model that you have to calibrate based on new observation is a model that's flawed, severely flawed, that you can't really use for any accuracy. But they think, well, it didn't work in the past, but it will work in the future because Professor, I don't know, so-and-so helped us. It doesn't work that way. You have to find something more robust like a heuristic. How many times have we recalibrated the speed of light? Okay, did we hear the recalibration this morning? Someone recalibrated the model? No, come on. So science is really something that takes very seriously what happens out of sample. The Planck constant has not been recalibrated. All these things we know, right, have not been recalibrated. We're improving on the models. But in finance, in economics, they keep rechanging the models, all right? Well, it means it's not models, they're forms of entertainment. Right? They cannot possibly be of anything, use of anything. Right? So I was proposing the tricks to work. If you work without, you don't have. When we did the measure of violence with the shadow mean, we said, if there's a third world war, okay, we wrote the paper before the Turkish guys got a little wild, but if there's a third world war, will it change our paper? No, on measurement of violence. If we had a century of peace, will it change our paper? No. Okay, then we're comfortable with our methodology, but you can't say that for a lot of financial models. They have a breakpoint that's one variable. Anyway, so simple heuristic. Let's start with a heuristic. Okay, so I went to work for the International Monetary Fund. I'm being filmed, so I have to be very nice. Except to say that it's in Washington, D.C. I don't know if many of you have been to Washington, D.C. Ain't London, all right. So that explains to you something. And there's also a culture there that dislikes things that are simple, right? So we wrote that one, and it was promised with a team, and spent all this energy. I was not paid, by the way. So all this energy, and hopefully someone told me that promised me. They said that in 2029 they're thinking of studying it, right? So the project, all right. So what is the heuristic? It's very simple. Let me tell you what you do. Have you heard of stress testing? All right. So when I went to the IMF, actually it's a joke. It's a very interesting story how I went to the IMF. There's a fellow called Dominique Strauss-Kahn, DSK, you know, all right. No, don't laugh. Reserve your laughing for in a few seconds. So he started talking about black swan. So they contacted me about black swan, and I'm allergic to the notion of black swan. Book says, this is for books, whatever. This is not the TED conference here. You're going to talk to me. I'm like a car mechanic. We talk about how to fix carburetors, you know, increase this thing. So I like to talk about nuts and bolts, not abstract ideas like black swan, schmack swans. All right, keep these, you know, go down next time, talk about it in Davos. This is not my business. My business is mechanics, all right, that we're going to see. So, very strange. So, okay, would like to see. And then, I don't know if you heard, there's a hotel called Sofitel in New York, in which interesting things happen sometimes. And then, between my meeting and that, all right, the Sofitel happened, and the following week, a lady came up who was pregnant, all right, to New York to meet talking about the project. And then as she showed up, the first thing she told me is, it's not from him. that was he's not the father. Say, okay, I didn't ask anything, right? So that's my story with the IMS. So I went there to counter, or at the invitation of a fellow who disappeared for reasons you know, all right? To counter the idea, I want to be like a car mechanic, you know, offer him something, you know, that works, right? Technical, right? So the heuristic, so offer the heuristic. I said, what do you do with stress testing? So very simply, that time they had Dexia passed the European Central Bank stress test, your competitor, of course, not as skilled, and they don't have, you know, the depth and realism, all right, that's present here. So European, I'm serious, all right, I'm honestly, I can talk from experience. So the European Central Bank, you know, they did the Dexia, and they declared Dexia phenomenally safe. Flying colors. How many hours before liquidation? Okay, so visibly why? Because when you do stress testing, people think it's not parametric. It's the most parametric thing. You're coming up with a number, an arbitrary number, okay? It doesn't tell you anything. If you're going to blow up beyond that number, you're going to see it in that number. And people know what number you stress test to, so they game it by having the risk beyond, okay? Aha. So we came up with a very simple idea, the simplest idea. You bring, show us how you do stress testing, and there are like as many methods of doing stress testing as there are streets with weird names in Washington, with, so. And all of them. You take, say you have one, some of them have a driver, and then you have a cluster thing that move with it. Some of them have different clusters and stuff. Okay. So like you move only one number or you move a cluster of numbers. Okay. All that, who cares? Whatever you're doing, do it 3 times. What? Yeah, do it 3 times. Why 3 times? Do it 3 times. So you do it 3 times. Guess what you get? What do you get from that? You get if you have acceleration. So you know if they're going to be harmed by an event that's way outside the stress test, particularly if it's slightly above the upper bound that you've tested for. It tells you the structure of the thing, and the ratio of the 2 numbers can be used as a very simple heuristic. You start looking at doing this on that stress test. There's actually some, okay, so someone came in and said, well, what if we have the wrong model? You can use the worst model you want. CVAR, you can apply it to CVAR. You bring CVAR and you tell them, what is CVAR sensitive to? Give me the 4 variables that enter. And do the same on these variables. Raise it 25%, lower it 25%. Or raise it, based on observe, 2.5 mean deviation, lower it 2.5 mean deviation. And then you can see if you have acceleration of one way and not the other. In other words, if you say I have one parameter, sigma, I put it in my CVAR, okay? I raise sigma 10%, my risk doubles. It's often the case, huh? You lower it 10%, your risk goes down slightly. You go to the cemetery, so you know, okay? So this is pretty much the technique to get the stress testing using this very simple graph here. That's it, this graph here. You do the stress test, and you can see if you have acceleration very easily, all right? So instead of focusing on one number, focus on 5, 3 or 5. You can do S5, or we call it S5. So it's as simple as that. Okay, now someone came to me and said, okay, what if I have the wrong model? Okay. Say, okay, who cares? What? Yeah, you can use a value at risk is junk, but it still gives you information there. Why? Let's think about it. If I have a child and I have a wrong ruler and I'm measuring the height of the child, okay, the wrong ruler will give me the wrong height. But will it tell me if the child is growing? Yeah, that's all we need. So the model needs to be, by theorem, we showed the error in the ruler. It has to be very, very bad for it not to show acceleration of risk. So this is the interesting thing. It's sort of like, we're coming back to a very simple measure like the frisbee, or not frisbee, the baseball thing, looking at the ball. It's so simple, right? So it works, and then we tested, if you use bad value or bad parameter, bad model, bad distribution, all of this, all right, good enough. It gives you the acceleration. And we actually proved that the model has to be very bad for it not to show. So your stress testing, okay, of course, has to span the right variables. So this is what we get out of this, okay. I don't know how much more we have. We have
5 or so.
5 minutes, okay. So this is the heuristic, okay. So we can generalize from that. Now we can take it one step further. Hold on, if I know how to maneuver with this, we can take it, into a lot of things about figure out, for example, if something we call barbell, it's a linear combination of very conservative plus very aggressive, outperform a medium strategy. I can show immediately why here, because it's a convex transformation, so uncertainty raises your right tail without your left tail. You see, if you increase in uncertainty, it's not going to stick up in both your tails, only one tail, which is the right one, the positive one. So you can do a lot of things with this. And then we kept generalizing to something like size, all right? Very simple. You know the liquidation of Kerviel? They had to liquidate how many billion? 55 billion. So it cost them 10% to liquidate, 8% to liquidate. The market dropped 10%. If they had a tenth of the size, would the liquidation costs have been that large? No. So visibly, you have a concave function of size, which comes automatically from the square law of execution. Actually, it accelerates when you have a larger portfolio. You can look at something in the UK, I think in the UK or something, I pulled it out from bridges and tunnels. Why is it that as your size gets larger, your costs become higher per unit? Okay, well, you have a concave function of size. That's it. You can pull a lot of things that are too big to fail from that. Okay, so very quickly, you can also use this of how models fall apart. Okay, why is it that models fall apart? Because, all right, there's some math involved, but let me give you the intuition. Okay, a lot of people say it's the wrong model, had wrong assumption. Who cares? I don't care about having a wrong assumption on a model. All I care about one thing, all right, is if I have a wrong number in the model, okay, that it's not concave. That's it. So there's no big nonlinearity. If it's linear, that's fine. Then you eventually will catch up with it. Is that you don't have nonlinear error in the model. I mean, track the ordinary doesn't falls apart in a tail. And you can test these. Okay, there are a lot of model error, but the most significant one is considering that something is non-random when in fact it's random. And that problem can be generalized to economics. This is how you model error. Is take for example things like Ricardo's paradigm, right? Where he had that story of wine versus cloth. Okay, he uses wine versus cloth. If you randomize both of them, you end up with a different allocation than if you have it static. You see. So that why? Because you have a nonlinear reaction to one of the variables. So you can immediately see which models are wrong from that. And that measure is called omega or something, which is that convexity effect is, okay, I give the example of a grandmother in anti-fragile. If I have my grandmother, to figure out if she's fragile, it has to have negative second order effect to temperature. So the best way to test is, what would you rather have, your grandmother at 70 degrees Fahrenheit for 2 days? All right, or one day at 0 degrees, the other at 140 degrees. All right, so for an average of 70. So if you have a concave function around the average, all right, then your model error, okay, is going to underestimate the effect of parameter uncertainty on your output, and you can track that. It's the same, almost the same heuristic that you can apply to model error. Make something, average the model across two parameters and see if you have a different function. That's pretty much what we're offering here in fancy terms, which is other heuristics to detect model error, you see. And with that, you could have some mileage, but I think I'm going to go straight to the conclusion. All right, this earlier was a very simple heuristic, so you're not going to remember a zillion things. But the same heuristic can be applied to model error. Okay, and we can talk about that in the Q&A. So let me very quickly conclude that most people think that we should not mathematize economics, mathematize finance, because it's and what we say, no, we should mathematize it by going to the foundation, all right? Mathematics is not about producing numbers. It's not with scientism. It's rigor, okay? So rigor, stay with the foundation. We have now years of statistics, more than a century, with a lot of foundation. So if you stay compatible with those foundation, and you'll find that will take you into territory that's completely opposite to the pseudoscientism that prevails today in measurement of risk and stuff like that. So stay within the orthodox framework. And it works beautifully. And you realize that a lot of stuff in economics, people know it's nonsense, but they do it because to get promotion, because of the system. But in the end, if you produce robust work, they will eventually adopt it, because you can't fool science for too long. Anyway, thank you for listening to me.
thank you, Nassim, for that fantastic talk. Now, the camera's off now.